Hey guys, so in this video we are going to be deriving the famous uncertainty principle, or at least we will derive what is called the generalized uncertainty principle, from which we get the famous Heisenberg uncertainty principle. And we won't actually get quite to the Heisenberg uncertainty principle because we can't do that until we learn more about how position and momentum are treated in quantum mechanics. But we'll get pretty close and I'll show you where that comes in. The first thing is I do have two quick notes about about things that we've discussed before. So I want to go back to the last video with the postulate that we just had, that if we have some quantity q, right, the expectation value, let me rewrite that, the expectation value of q, right, which is like the average value of q, is going to be the inner product of psi and q hat psi, right? This is again with the particle being in the state psi. And I want to talk about that. Talk about that for a second. Because there are two important things that we can get from this. Number one is another reason why the operator Q hat has to be a Hermitian operator, right? And so I'm gonna combine two of our properties of operators that we know. To start off. Well, this is not just operators; these are Hermitian conjugates in general. If I have A and B, right, the inner product of A and B is the inner product of B and A Hermitian conjugate. Although, remember, the inner product is going to be a scalar, so the Hermitian conjugate is just the complex conjugate. Right, that's one thing. The second thing is we know an operator, if we have any operator, if we have A and Q hat B, right, doesn't matter if it's Hermitian or not, will always be true. This will be the same as Q hat dagger A and B, right? Well, now we know, since we want Q to be a quantity, an observable quantity, we know that Q, sorry, Q has to equal the expectation value of Q has to equal the expectation of value of Q complex conjugate. This just means that the expectation value of Q is real, right? This is something that we have to have on a real system, a real observable. It's got to be a real value. It can't get, the position being I. That would not make much sense whatsoever. Right? Well, now, if we look at this, well, this one right here, we know is psi inner product with q psi. And the complex conjugate of that will be, well, just looking at this one over here, right? To get the complex conjugate, we just switch them, right? You could say that B complex conjugate is BA, right? Either way, complex conjugates will work like that, right? And so this would be the same as Q hat psi psi. Well, looking at this one, that means, apparently, because we just have this one condition, that, sorry, not psi, that Q hat dagger must be equal to Q hat. Q hat has to be Hermitian, which is something that we already know. I gave you reasons before, but this should be an even more concrete one, right? With a very simple condition that observable values have to be real. Even though that was actually sort of a condition that we had before in Hermitian operators. But this is just to show, instead of saying that for a Hermitian operator, observables have to be real. Now we're going the other way. In order to get a real, to have something that's guaranteed to have a real expectation value, the operator has to be Hermitian. Okay. Second thing is just a notational thing, which is going to be very common. Textbooks love to use this notation, the one that I have been using. But it is not really a great notation, and I will show you why in a second. And so this is the notation we have been using for for these inner products, right? But a lot of textbooks, or maybe not a lot, but some, will use this notation instead. Instead of this, they'll use psi q hat on the inside, psi, which actually does make a lot of sense, considering that, and I may have touched on this before, just saying q hat psi doesn't make a ton of sense, right? Because psi is just the label on this vector, right? The vector is the object itself, right? So, a quantum mechanics book, Griffiths, that a lot of schools use, he relates this psi to like the serial number. It is just something that labels the state, right? You could have this 1, which some right, they'll use 1, 2 to correspond to the first state, the second state, right? Well, if you had a q hat acting on it, right, q hat acting on the second state, that's not like the state with q hat acting on the number 2, right? No, that's not what it's saying. I don't know if that will hopefully make sense to you. That this psi is just a label, so it is much better to write this as q hat acting on the ket vector psi, right? This is really the best way, but a lot of textbooks use this, and it is a bit more convenient. But especially another reason is once we get into like linear algebra, you will see why this notation is so much better. So just to show you, you may see this, and honestly, it is actually a better notation, but I'm using what I believe is sort of the more standard one. But this one, where the expectation value of q is the psi bra vector, q hat psi ket vector, right? Just because this statement doesn't really have much meaning on its own, right? It's an operator acting on a vector. It's not some vector labeled by an operator and whatever psi is. Psi being just a label on the vector. Okay. So now we can go ahead and look at the uncertainty principle and the proof of the uncertainty principle. Now, I don't know who originally did this proof. I think it may have been Heisenberg. But either way, right, we're gonna do this proof, and I want to warn you ahead of time. It is a very complicated proof, and not very complicated, but it is pretty complicated, and it's got a lot of algebra. You may not fully understand every step that I make. I want to try to make it as user-friendly as possible, to make it as easy as possible, but I'm just letting you know that that you might get lost somewhere, and so the best thing to do either is to go back, try to figure out where you got lost, or understand as much as you can. And the biggest thing is at least knowing that the uncertainty principle does not just come out of nowhere, right? There is actual reasons behind it. There's a proof that really only requires the quantum mechanics that we've done up to this point in the course. So the first thing that to do is remember what the uncertainty principle is trying to do. It's trying to find a lower bound on the uncertainty, right? If I have two quantities, I've got A and B, and I've got the standard deviation in A, and the standard deviation in B. And the goal of the uncertainty principle is to say that this is not less than or equal to say that this uncertainty is greater than or equal to something, right? That there is some inherent uncertainty between two quantities, right? You've probably heard of the Heisenberg uncertainty principle with position and momentum, although it actually gets more general than that, and that's what we're going to drive. We're going to drive the general uncertainty principle, and I'll talk about the Heisenberg uncertainty principle, but we haven't fully understood position and momentum in quantum mechanics yet, so in the next section I'll get to showing exactly why the Heisenberg uncertainty principle is what it is, but it's based off this proof, and I'll use that proof when we get to there in section 3. Right, and so the thing is, for this proof, it's actually going to be easier. Instead of showing that sigma A, sigma B, we're actually going to use the variances, which is just the square, right? And so then we will be able to square root the equation at the very end, but sigma A squared times sigma B squared, and we're going to find some lower bound on this. And I'll rewrite that. I'm going to rewrite this whole thing, make it look a little bit better, and then we'll get started with the proof. So this is sigma A squared times sigma B squared, which is what we are looking for. Okay, so hopefully you've reviewed that video on statistics, and if not, I'll have the link in the description. I'd love if you guys can go review that video because it will be very important, and you'll need to know some of that stuff for this video. So the first thing to do in this proof is show what sigma A is. So this is sigma, the standard deviation, in A. And if you remember, we know that the standard deviation squared is going to be the expectation value of the variation, of the deviation, delta A, of the deviation squared, where delta A is going to be A, the observable, the value of the observable, minus the expectation value of the observable, right? It's how much the actual value is different from the expectation value. And so now to get one of these expectation values in quantum mechanics, we're going to have to turn delta A into an operator, which is going to be pretty easy. We just put an operator hat, right? So delta A, the operator, is equal to the operator of the observable, right, A, minus the expectation value of the observable A hat, but we don't actually need that hat. And the reason is, I believe we talked about, back when we talked about operators, and also just what expectation values are in general, expectation values are scalars. And a real scalar, hopefully, if A is Hermitian, right? Which it has to be a reasonable observable, right? And the expectation value is a real scalar, and multiplying by a real scalar, right? If I had I think I used the example of having 2 hat acting on some function f of x, right? This is just 2 times f of x, right? The operator version of any real any constant, any scalar in general, is just multiplying by that scalar. Now, 2 is a real scalar, and so is, right, hopefully this expectation value of A, which will mean that it is multiplying by a real scalar is a Hermitian operator. So this is another thing to point out, that delta A hat is Hermitian. This is going to be important in a few minutes. Excuse me. So now, if we look for the expectation value, or for the expectation value of delta A hat squared, right, we can first write out what is delta A hat, or delta A squared hat, right? This is just delta A hat, right? Applying the operator twice. And when we do this, we can also write this out as A hat minus expectation value of A times A hat, or sorry about the cough, A hat minus the expectation value of A, right? So this is how we will write A hat squared, right? And if we're trying to get the standard deviation, or the standard deviation squared, sigma A squared, this will just be the inner product of psi and delta A hat squared psi. Right, I know it's, again, the same sloppy notation that I had talked about before, but it's a more commonly used one, and it is convenient. It's very compact, so this is the one we'll be using, at least for right now, but just I wanted to show you the other notation so you knew it and understand that it's maybe even a little bit notationally better for this situation. Right, and you can also write this as psi delta A hat psi. Now here's the important thing. Delta A hat is Hermitian, which means we can bring it to the other side of the inner product. So I'm actually going to do that with only one of these. And so I will write this as delta A hat psi, inner product with delta A hat psi. Right? Where this is how we write delta A hat. Right? And now I'm going to say define f the f vector to be delta a hat psi. And so we can write this as the inner product of f with f. Okay, so this is going to be our one definition that we're going to have. And I'm just going to do this quickly I'll do this in a different color with sigma b squared. So sigma b squared is going to be the expectation value of delta b, where b is another observable, squared, right? We'll say delta b hat is going to be b hat minus expectation value of b, right, where this is just a scalar, so it's already an operator, just multiplying by it, right? And then we can square this whole thing. I'll just write the first part of that, where delta b hat squared is delta b hat, right? And so then we can write that sigma b squared is psi inner product with delta b hat squared psi, which, using the same logic we have here, this is using the fact that delta b hat is also Hermitian, right? This is delta b hat psi inner product with delta b hat, sorry, not inner product with psi, inner product with delta b hat psi, which I will call G inner product with G, where we define, and I'll put this up here as well, G, the G vector is delta b hat acting on psi, right? So I'm going to sort of circle the important parts here to make sure that we can find them easily, and then go back to them when our proof needs them. So I'll underline these two parts too, because those are going to be important. Actually, I'll just go circle them as well. Okay, we are going to come back to this. Now, I want to note that sigma a squared, sigma b squared, right? If we just look at sigma a squared is f inner product with f, and sigma b squared is g inner product with g, this is f product with f times g inner product with g. Okay, so I'm going to start up a new page here, and we're going to keep that in mind. And right now I need to show you guys two very important inequalities. Okay, these are going to be very important inequalities for proving the uncertainty principle, because again, we want to get an inequality at some point. Right, so this first one is called the Schwarz inequality. SCHWARZ, the Schwarz inequality. And I will give you sort of a geometric reason of why this inequality is. Just thinking about dot products. And actually there's a version of this for dot products, and I'll show you that one first. And then, knowing that the inner product is just a generalization of the dot product, if it applies to the dot product by the same logic that we use for me to geometrically show this inequality, the same logic will apply to the inner product. Now, maybe you know from a physics class, or a math class, a dot b, and I may have shown this on our video of vectors, if I have a vector dot on b vector, right, this is going to be the magnitude of a, not capital, magnitude of a times the magnitude of b times the cosine of the theta between them. Right? And this makes sense. If I've got a vector A and I've got a vector B, right, their dot product is actually going to be the length of A times the length of B that is parallel to A. So just this part, not the whole length of B. Or not, sorry, not I don't know why. I didn't not like that. Sorry. If we have the part of B that is parallel to A, so it would be this much. So it would be A, this length, times that length. Right? And so the biggest this dot product can ever be, right? The biggest this dot product can ever be is where A and B are parallel. If and only if A and B are parallel, A dot B is going to be the magnitude of A times the magnitude of B because theta is going to be 0, right? Anything else, it's going to be less than magnitude of A times magnitude of B. So we can write this inequality as A dot B is always going to be less than or equal to the magnitude of A times the magnitude of B. Or if we want to square both sides, A dot B squared is always going to be less than or equal to, again, this is just based on geometry, right? A dot B squared is less than or equal to the magnitude of A, the magnitude of B. In the description, well, actually, first, let's go to the full Schwarz inequality. So based on this, just like we can do this with dot products, we can also do this with inner products, where, oh, and hopefully you caught this, there should be squares here, right? With inner products, we know that if I've got two vectors f and g, if I have f inner product with g, f inner product with g is always going to be less, or actually if I have this norm squared, do it like that, f inner product with g norm squared is always going to be less than or equal to the magnitude of f norm squared times the magnitude of g squared, right? Remember the magnitude just being the length, right? This is just showing for complex numbers instead of just real numbers, where squaring will be, squaring is makes it positive. Here we have to take a norm squared to make sure it's positive. Right? And if we want to write this, we know f norm squared is f inner product with f, g norm squared is g inner product with g, right? And so we know that f g norm squared is less than or equal to f times g. This is the Schwarz inequality. And I'm not, I gave sort of a mini proof to it. I would not really call it a real proof. However, if you want to see a real proof, I'll have one in the description. It will it uses a slightly different notation. It uses bars instead of stars for complex conjugates. But in general, it's I mean, it proves the same result. And so this is all I'm going to give. If you just want to go with me on the Schwarz inequality, that's okay, but we're going to use it for this. Hopefully you see why we're going to use it, right? Because this is our sigma a squared, sigma b squared. Right? The next inequality, I don't know if it has a name, it's just an inequality about complex numbers. Right? And what this is, right, is I mean, really, it's just a general statement about complex numbers. That if I have, let's see, if I have a complex number z, right, and I want to look at z norm squared, right, we know that this is, if z is a plus bi, right, then z norm squared is a squared plus b squared, right? Where we will call a is the real part, re, real part of z squared, plus, and then b is going to be the imaginary part, im, the imaginary part of z squared. This is just going to be the notation that we use for this, right? So z norm squared is the real part of z squared plus the imaginary part of z squared, right? And so I'm going to erase this. Well, you see why it's this, right? But now I'm going to look at, well, if this is, so this is the real part of z squared plus the imaginary part of z squared, this has got to be greater than or equal to the imaginary part of z squared, right? Because the real part of z, imaginary part of z, those are all real numbers, right? A and b for a plus bi, those are real numbers, right? So this is just saying a squared plus b squared is greater than or equal to b squared, which has to be true as long as a squared and b squared are both positive, right? Because a and b are real numbers, right? Well, now I mentioned this in the complex number video, and I'm just going to rederive it here. If I have z equals a plus bi, I want to figure out what b is in terms of this, but not in terms of well, I could do z minus a over I, right? But I don't want to do that. I don't want to include a, right? I want to get b solely in terms of z. So for this, we may want to use the complex conjugate, z star, which is a minus bi, right? And so now, if we want to find what b is, right, first I'd say let's do z minus z star, which is going to be 2bi, right? And so b is z minus z star over 2i, right? And so now remember, b is the imaginary part of z, right? And so now I'm going to rewrite our complex number inequality as this. Z norm squared is going to be greater than or equal to, it's the imaginary part of z squared, which is 1 over, actually I'll put the 1 over 2i. 1 over 2i z minus z star, and then all of this squared. Okay, and now one more thing to do with this, and I'll do it in orange. Okay, if z is, I don't know, let z be f inner product with g, right? So f inner product with g norm squared, put it down here, f inner product with g norm squared is got to be greater than or equal to, okay, 1 over 2i z, which is fg, f inner product with g, minus z star. And z star, remember, if you just if we take the complex conjugate, we just switch we switch f and g. So g inner product with f, right? And then all of this squared. This is our second inequality. We have two inequalities here. So hopefully you've got this stuff down. I'm going to erase the stuff in red over here, so we can show something, right? And now this is just a property of inequalities. If I have, I'll use A, B, and C again just because that's, usually the best letters to just use. If I have A is greater than or equal to B, and B is greater than or equal to C, then A is greater than or equal to C, right? And hopefully this logically just makes sense. If A is bigger than B and B is bigger than C, right, then A's got to be bigger than C or equal to, right, if we have the equal to condition, right? This is just mathematical logic. It's very simple logic here. right? And now look at B. B is this F inner product with G thing, right? This is F inner product with G. So F inner product with F times G inner product with G is greater than or equal to F inner product with G, norm squared, right? Sorry, this would be norm squared. And F inner product with G norm squared is greater than or equal to this thing, right? So our conclusion, and I've got to put this in white here. Our conclusion is that F inner product with F times G inner product with G is, which, just to remind you, is equal to sigma A squared sigma B squared, right? Is going to be greater than or equal to, because that's our A, right? This is our A, this is our B, this is our B, and this is our C, right? Is greater than or equal to 1 over 2I F G minus G F, all of that squared. Okay, and I'm going to circle or box in this part. This is where our uncertainty principle is so far, which is good because now we have sigma A squared sigma B squared has this lower bound of 1 over 2I F inner product with G minus G inner product with F, where F and G are the things that we defined before, right? So we're gonna go with this. So I'm gonna write this on our next page. So we have sigma A squared sigma B squared is is greater than or equal to. I hope I did write greater than or equal to, right? Yeah, it's greater than or equal to. All right, 1 over 2I FG, F inner product with G, minus G inner product with F squared. Sorry, not that squared, it's the whole thing is going to be squared. Okay, and if you've been watching this video straight, good job, but this is probably a good point for you. Once now we have this, we have a bit more algebra to do. This might be a good time to take a brief break and come back to the video in a few minutes when you have your mind refreshed, because this is a very tedious video. Okay, so hopefully you took a brief break and cleared your mind for a second. So now we can get back to this proof. So what I want to look at is I want to look at F inner product with G. I want to look at that in a little bit more specifics, and what I'm going to start by doing is bringing us back to here to look at what is F and what is G, right? So hopefully you have these down. That's why I had made a big deal of circling those in before, so we can go back and look at them. The definition of delta A hat, the definition of delta B hat, right, using this. And I'm just going to go, not really skipping steps, I'm just going to write down what you would get if you just combine all these equations together. FG equals, we should have A hat minus expectation value of A psi inner product with B hat minus expectation of value of B psi, right? But we know that we can these are both Hermitian operators, so we can bring them to the same side of the inner product, right? We can switch sides, so I'm actually going to bring this A term over to this side. So see if I can squeeze this in here. So psi inner product with A hat minus A B hat minus expectation value of B psi. Okay. Now, I'm going to FOIL this out, right? Just use the algebra tricks that we've used. Now, be careful, right? Because some people will be tempted, actually, to be very cautious. Order does matter here, at least in terms of the operators, right? We know that numbers, if I have two numbers, x times y equals y times x, right? For any two numbers. We know that that's true. That's a property of numbers. That's the commutative property of numbers. For operators, we have not concluded that they commute, that a hat times b hat equals b hat times a hat. In fact, in general, that's not going to be true, and I know that's kind of mind-blowing for a lot of people. That there's things that 1 times a times b is not equal to b times a, but it's true, and I'll show you that as we move along. Especially in our next section, we will have some focus on the difference between a hat times b hat and b hat times a hat. And actually, we'll get to a little bit of that in this video, right? But we know that if I just have a expectation value times any operator, right, times q hat, as long as q hat is linear, right, q hat a. This is a property of linear operators, right? Because a expectation value of a is a scalar, and we know that was one of our definitions of linear operators. And remember, a hat and b hat both have to be linear operators, right? So with that, let's FOIL this out. Psi, inner product with. Okay, we have, let's start with a hat, b hat. And order of addition doesn't matter, but order of multiplication may. So a hat, b hat, not b hat, a hat. Right? The rest of them, everything else, the order doesn't matter, but this part, the order does matter. You'll see why I'm stressing that point in a minute. Okay, a hat, b hat, minus a expectation value of a times b hat minus let's see, expectation value of b times a hat, right? We could have done a hat times the expectation value of b, but order doesn't matter in that case, right? Plus a expectation value of a times the expectation value of b, right? And then this is all of this big operator is acting on psi, right? And now let's break this up. And this is, I believe it's a property of inner products that I did talk about when we talked about inner products, that there is a distributive property. And if not, now I'm talking about it. But I believe I did talk about it before. That if I have the inner product of, I don't know, I'm running out of letters to use. U inner product with v plus w. This is u inner product with v plus u inner product with w, right? Or you could do it with a minus sign, right? U inner product with v minus w is u inner product with v minus u inner product with w, right? That's just like multiplication. I think I did talk about that before, but in case I didn't, now I'm talking about it. And so now we're going to use this property to split this up. Instead of one giant messy inner product, a bunch of simpler looking inner products. So this is the inner product of psi and a hat, b hat, psi, right? Minus inner product of psi, a hat, or expectation value of a, b hat, psi, minus psi, expectation value of b, a hat, psi, plus psi inner product with a hat, or expectation value of b a, expectation value of b, psi. Right? Now, here's what to look at. Remember, we can take that's another property of inner products that I believe I talked about, where if I have psi and I'm product with some constant times psi, or some constant times q hat times psi, or whatever, right? You can take the constant outside of an inner product, right? Or not just a constant, but a scalar, right? It doesn't have to be a constant. I have to be careful with that. Actually, no, it does have to be a constant. My bad. But in this case, in at least what we're dealing with right now, scalars, all scalars here are going to be constants, at least for what we're dealing with right now. In our next section, it will not be like that. But when I'm saying that, the expectation value of A, it doesn't vary. It's a defined thing, right? Expectation value of B, right? So we can take those out of the we can take those actually out of the inner product, right? And so let's do that, right? Well, first, now let's look at this. What is, and I'm going to leave the hats on here just because it's going to be important. This is the expectation value of A hat, B hat, right? That's what this expression is. Minus, okay, A times the expectation value, right? Psi inner product with B hat psi is just the expectation value of B, right? Minus, and you'll see why I'm leaving the hats on here. It's just important, just so you don't, just so you remember that you can't switch the order. Minus B times the expectation value of A, right? And then plus here, this is, we can take A and B outside of the inner product, and we're left with A expectation value of A times the expectation value of B times psi inner product with psi. Psi inner product with psi is 1, right? That's normalization, so this is A, B. Right? Well, remember, AB is the same as BA, but even if it weren't, we could do that, right? But it is. And so this, right, and remember this is F inner product with G, is A, B minus expectation value of B times the expectation value of A, although I can write it like expectation value of A, expectation value of B, because these are just scalars, right? Scalars commute, right? And so this is FG, just to remind you, right? Now, I'm not going to do this whole thing again with GF, right? And here is the reason why. If I look at GF, right, that's just replacing A and B, right? GF is just replacing A and B. That's FG. F is right. If we just start this, okay, I'll do it this way. I'll just start it. This is going to be B hat minus B, which these will be complex conjugates, of course, but that's not going to be the useful fact here. All right, B hat minus expectation value of B times psi, inner product with A hat minus expectation value of A. Sorry. And if you do the exact same steps in algebra, just remembering that you can't that you cannot switch A and B. If you do the exact same steps in algebra, what you'll eventually get is you'll get, this is going to be B hat, A hat, right? Expectation value of B hat, A hat, minus, and remember, these you can switch the order, these you can't. Operators may not commute, right? A hat times B hat is not necessarily the same as B hat times A hat. We know it works with numbers. I know I'm saying that a lot, but it's so important that you realize that, because you'll see it. That's going to be the biggest part of the uncertainty principle to tackle. Although we are almost done with the derivation, right? We have A hat minus A B, right? Okay, so hopefully you have all of this down, right? All of this this work over here, because I'm about to erase it. And if you do not have it down already, just make sure you go back and write it down, so that you can be, so make sure you go back and write it down to make sure that you still you can look at where we got any of this from. So now if we rewrite this, so this is going to be greater than or equal to, so if sigma a squared sigma b squared is going to be greater than or equal to 1 over 2i. And now let's figure out what this thing in the parentheses is. Well, fg, right, is a hat b hat, expectation value of ab, minus a b, right? And actually I'm going to probably move this parentheses out a bit. So, and then minus b hat a hat, looking down here, the expectation value of b hat a hat, then plus, right, because we're minus a minus, plus a hat, our expectation value of a times the expectation value of b. And then this is going to be squared. Well, we know that this is equal to that, right? So they're gonna cancel. And then one last like side note here. If I have a hat b hat minus b hat a hat. Again, you see this is going to be important because a hat and b hat may not be the same as b hat a hat, right? This is psi inner product with a hat b hat psi minus psi inner product with b hat a hat psi, right? And just because we know, just like how we did before with the inner products, we had one big inner product and we split it off because we were adding and subtracting, we can just combine these inner products now. This is going to be the inner product of psi with a hat b hat minus b hat a hat psi, right? Which is going to be, this is just going to be, so I'll keep these, right? And this is going to be the expectation value of a hat b hat minus b hat a hat, right? And so now if we go look at this here, back in our uncertainty principle, sigma a squared, sigma b squared is going to be greater than or equal to and this is, so if we want to rewrite this side of the equation, it's going to be 1 over 2i times, well, we know what this is now. This is the expectation value of, actually I don't even need this parentheses now. This is going to be the expectation value of a hat b hat minus b hat a hat. And this is squared. Now, lastly, and I'm going to, now that we have everything done, I'm going to erase this bottom part too. Hopefully you have it down. We actually have a name, a mathematical term. You may have seen this in like a linear algebra class. We'll deal a lot more with this throughout the course. A hat b hat minus b hat a hat has a special name, or a special representation. It's a commutator. So we write this with a bracket, so I'll actually end up turning these into parentheses just so you don't get confused. It's a bracket a hat, comma, b hat. Right? A hat, comma, b hat, right, is called the commutator. Might have two m's. I am not entirely sure. Yeah, I think it has two m's. So the C-O-M-M-U-T-A commutator. Okay, and it's also might be important to know a hat b hat commutator is equal to negative b hat a hat, right? If you just switch a and b, right, you get the negative of the equation, right? And this is important because if like the commutator, I don't want to erase that part. I just want to erase this. If the commutator of two numbers, right, or two scalars, if I have some, functions f of x, g of x, right? These are scalars. This is equal to 0, right? Doesn't matter if they're constant. Scalars commute. Just like if we had, expectation value of A, expectation value of B, right? Saying they commute if one times the other is the same as the other, is if f times g is the same as g times f, right? A comma b, this commutator, right, is equal to 0 because they're scalars. But if they're operators, it may not be, right? And so the last thing we're going to do, and then this is the generalized uncertainty principle. Sigma a squared, sigma b squared is greater than or equal to 1 over 2i times the expectation value of the commutator of a and b squared. And this right here is the generalized uncertainty principle. Now this may not look super familiar, but now I will plug in an actual value for a commutator. Right? If we take and we will find this in our in the next section, the end of section 3, not exactly at the end, but we will find what the commutator between the position operator and the momentum operator is. And now notice, you might think that, if I have an I here, right, squaring it will give me a negative number. Of course, uncertainty, right, because these are real numbers, they're squared. This is going to be some positive number is greater than or equal to some negative number, of course. However, the important part of this I here is that this commutator is actually pretty much always going to have its own factor of I, right? And so they'll cancel out. So just like we'll see here, the commutator between the position operator and the momentum operator, we will find in the next section, ends up being I times h bar, right? And so sigma x squared, sigma p squared is greater than or equal to 1 over 2i times I h bar squared, right? So, that's going to be, if we just cancel out the i's and then square it, h bar squared over 4. Or if we square root this equation, sigma x, sigma p is going to be greater than or equal to h bar over 2. And this is the famous Heisenberg uncertainty principle. I know it's based off this commutator, but we will find that a little bit later. So hopefully this makes sense. And one other thing to note, if you switch x and p, right, it shouldn't matter because standard deviations, these are just numbers, they should commute. And if you switch a and b, you get a negative sign, but you're squaring it, so the negative sign goes away, right? The difference, if I have a negative something squared or the positive something squared, it doesn't make a difference. So this is the same as sigma b squared, sigma a squared, right? The only thing that doesn't commute are these operators, and we will soon be able to find out why exactly these operators don't commute. Okay, I'll see you in the next video.